Ladies and gentlemen, good evening. I'm Paul Davies, Director of the Beyond Center for Fundamental Concepts in Science at Arizona State University, and welcome to this special Beyond Center event, a panel discussion. And before we proceed, could you just put your cell phones to silent? I'll give you a moment to do that. The Beyond Center's motto is confronting the big questions, and one of the biggest of the big questions of existence is, are we alone in the universe? For most of the history of mankind, this question has remained firmly in the province of religion and philosophy. But in recent decades, it's become part of science too. I've been interested in whether or not we are alone in the possibility of life beyond Earth ever since I was a student in a different century. And in those days, there was an enormous skepticism about the possibility of life beyond Earth. One might as well have professed an interest in looking for fairies. Francis Crick, for example, said life seems almost a miracle, so many of the conditions for it to get going. Jacques Monod said that we'll at last know that we are alone in the universe, out of which we emerged by chance alone. Now the pendulum has swung the other way, and so already by the 1990s, Christian de Duve was able to write that life seems almost inevitable and would crop up wherever conditions permitted. And he had this wonderful phrase, life is a cosmic imperative. But in spite of this new upbeat sentiment, we still have no direct evidence for any life beyond Earth, let alone intelligent life. And we remain almost completely in the dark about how non-life turned into life. Was it a bizarre chemical fluke, as Crick supposed, in which case we would be unique in the universe, or is it, as de Duve said, a cosmic imperative? Well, the best way to find out is to go and look, and that is the agenda of the subject of astrobiology, and we meet here because of the NASA Astrobiology Science Conference, which this year is hosted here in Mesa. And my thanks to NASA for facilitating this evening's event, and to the coordinators of the NASA Astrobiology Science Conference, AbSciCon. So I'm addressing these remarks to members of the public who may have joined us, and a special welcome to you. Otherwise, the people you see around you, I think, are all delegates of AbSciCon. So the way we're going to handle this evening's event is that we have over here a distinguished panel of experts who I will introduce one by one in a moment, and they're going to come up to the podium and give us their 5-minute sales pitch as to where they think we're going to find life beyond Earth. And then when that's over, I'll facilitate some conversation between the panelists. And when that is over, we'll open the floor to the audience, and we have 2 microphones there for you to come forward and ask your questions. So I hope that's pretty clear. And the panelists are sitting, not for any sexist reasons, but they're sitting in the order in which they're going to speak. And there's some logic to this, because we're going to start way out there and come in closer to home. And so first up here, we have Vicki Meadows. She's at this end. She's from the University of Washington and the NASA Astrobiology Institute. Then we have Brittany Schmidt of Georgia Tech. Then Svetlana Shkolya, which she tells me means scholar, from the Carnegie Institution. And then next to her is Sarah Walker. And Sarah's come all the way from America's largest and greatest university, which by coincidence happens to be right here in Arizona, not far away. It is, of course, Arizona State University. Had to get that plug in. Then we have Jacob Hack-Misra with the Blue Marble Space Institute. And last, but as you will soon find out, by no means least, Charlie Lineweaver of the Australian National University. And I also, as I mentioned, from Arizona State University. And seeing as we actually have 3 Australians here on the panel, it's only fitting to mention that today is Anzac Day, if that means anything to people in the audience. So without further ado, I'm going to ask each of our panelists to brave the steps. They've got to go down, up, and then back again without falling over. So be patient. I'm going to call upon Vicky Meadows to get the show started. Thank you.
Thank you for that introduction, Paul. My position I am taking today in this debate is to say that I think that the place where we will find, first find the second incidence of life will in fact be on exoplanets. And that may be a crazy position to take because exoplanets are literally light years away. They're very, very far away. However, there are some advantages to that. I'm sure many of my colleagues here are going to argue that it'd be much better for us to actually look in the solar system where things are nearby and when we can fly by and put probes down and study them. But exoplanets have the following advantage in that there are a lot of them. We think on average for the most common types of stars in our galaxy, there's probably at least 2 planets per star. Also, it allows us to look for planets that are more Earth-like, terrestrial planets, whereas we don't have any other examples of habitable planets in our solar system. So we can look for planets a lot more like Earth. We can also, and this is the main point, we can look for life on the surface of the planet. We don't have to worry about trying to find life clinging by its microbial fingernails in some kind of extreme environment elsewhere in the solar system. We can look for life that's abundant and happy on the surface. And so as a result, that life can produce a pretty large signal on the planet. So even though the planet is very distant, the signal may be very strong. And so we might have a very good chance of seeing it. So if we're going to look for the signal of life, one of the things we probably want to look for is photosynthesis. So photosynthesis, modern photosynthesis, harnesses carbon dioxide, water vapor, and sunlight, things that should be very common on the surface of a habitable planet elsewhere. So essentially, these organisms have been able to do this and to cover our entire planet because there's water and carbon dioxide and sunlight everywhere. So we see them in lakes, in oceans, on land, and in extreme environments, even hot springs and the poles. We find life there that photosynthesizes. So the photosynthesizers have essentially developed the killer app. They've managed to turn sunlight into food. And as a result, they've taken over the entire planet. Of course, we've managed to subjugate them in the form of salad, but nonetheless, they are a force to be reckoned with. And so the oxygen that they produce, over billions of years, microbes have produced this oxygen, and it has now dominates the atmosphere of our environment, our planet, and we can see it over very great distances. So if we were to look for this oxygen from photosynthesis, it turns out that for astronomers it's very easy because oxygen has a lot of absorption bands, a lot of ways that we can detect it through the visible to near-infrared region of the spectrum. And that is the region where we are going to be building our first telescopes. So that is certainly a place we would like to look, and oxygen sits right there in a place that we can look at. Oxygen is also mixed very evenly throughout our atmosphere. There's so much of it that you can see it even above the clouds, and even with techniques that look only through the upper atmosphere of our planet. And very soon, in the next year, in fact, we're going to launch a very large telescope called the James Webb Space Telescope, which will be able to look at planets passing in front of their star, and potentially habitable ones, and look for the signals of oxygen or its sister products like ozone in the atmosphere. We also are building ground-based telescopes that can be upgraded with instrumentation that will ultimately allow us to also look for oxygen and potentially ozone on planets around M-dwarf stars. And so this is coming in the next few years, basically. We also have targets that JWST can look for. The recent discovery of the TRAPPIST-1 system and the LHS 1140b planet have already provided to us targets that we know we can look for with JWST. So in essence, we're looking for planets that are more Earth-like, that have strong signals on them from photosynthesis, life that covers the surface of the planet. We have the instrumentation in the next few years to observe this, and we already have the targets available. And so for those reasons, that's why I think exoplanets, oxygen, and the James Webb Space Telescope are the reason why we will find life first on exoplanets.
Perfectly timed. Thank you. Perfectly timed. So next I call upon Brittany, who at Georgia Tech is apparently known as the robot woman.
Alrighty.
Oh,
Quite
the
the
balloons.
introduction.
We're really proud of the balloons.
Just move them.
There we go. I hadn't realized it was that easy. I'd have done it. I'll tell you what we might do. We'll bring them over here, perhaps.
But then they're going to be
There
in
you
front of
go.
somebody else.
No, all right. I can sit and hold them. Because I thought, it takes us up.
Putting those,
We're not going to charge you for the time spent messing with the
the
balloons.
Georgia Tech
you see,
engineering skills.
take another 30 seconds.
All right, well, hello everyone. So I am going to talk to you about the potential for discovering life on the ocean worlds, or the icy ocean worlds, of the outer solar system. And so how many Arizonans do we have in the room? Turns out I'm also an Arizonan. So if you're an Arizonan, you've looked out, especially here in Phoenix, and you've pretty much seen every day something very familiar. And when you look at Mars, you see something very familiar. So that desert landscape is kind of something that's kind of human and an experience that we've all had. And what I'm going to actually ask you to do is to unimagine that, to think about the Earth, in fact, in the 75% of it that's covered in oceans, and in fact the polar oceans, which are covered in ice. And so let's bring this home to another environment on the Earth that's very, very, shall we say, alien. And so our group's perspective, or people that work on icy satellites, we're looking at the potential of life in an alien ocean, but in one that's very, very much so reminiscent of the things that we have here on our own planet. So we're sitting on the original ocean planet, and if you haven't been to Antarctica or the Arctic, perhaps you've never seen it totally covered in ice, but it's really not so alien at all to imagine an environment like that. So when we think specifically about which ocean worlds we might think about, the one, at least for me, that rises to the top is the moon that's shown here, which is Europa. So Europa is not the largest, but is the innermost, meaning closest to Jupiter, of the icy ocean planets that orbit the giant planet. And so this place is a really remarkable world that's given a long-term source of energy from tidal activity. What we know about it is that it's an ice shell that covers up an ocean that might not be so dissimilar from our own. And so as we start to think about in the ways in which Europa, which is about the size of our own moon, in fact, just covered with this ice shell and ocean, might be much like our own planet, that's what I'd like you to think about here. So I'm going to give you kind of 4 ways that Europa and the Earth are very similar. So the first one, in fact, is water. So we talked a little bit about water here. Turns out that Europa has something like 2 to 3 times as much water as the Earth does. And so, in fact, we're not limited in any kind of way. Turns out what makes Europa special amongst the ocean worlds of the outer planets is that, in fact, it's so rocky. And so it's got what we would call the chemistry, or the right energy inputs into the system. And so those are the other parts that we think about. So in terms of the chemistry, so we've got water as our first ingredient. In terms of chemistry, we know we've got this silicate interior. So it's an interior much like our own. The data that we have so far suggests that it's got an iron core, it's got an outer silicate mantle, so very much like the Earth. And very importantly, because it has relatively less water than some of the other ocean worlds, that water is in contact with the rock below. And what might not seem apparent, but is one of the places on Earth that we think about for the origin of life, is at that interface between an active interior and an ocean above it. And so in terms of the juxtaposition of the chemistry that we have here on Earth, the ocean circulating through the rock below is a real potential source there on Europa. Finally, one of the things that we also think about is energy. So life depends on some source of energy, whether you call it energy or you call it disequilibrium. But basically, life is doing some kind of work. It's stealing energy from another system, and is doing that to produce biomass. And so when we think about planets, it's sometimes hard to think about how that might operate. On Europa, we think about energy in terms of the possible existence of hydrothermal vents. So these chimneys of activity where the chemistry and the water temperature and the energy are just right for life's origins and perhaps for its sustenance. And very importantly, when we look at the surface of Europa, it actually is a lot like Earth. It's the only other place that we've seen that has potentially active plate tectonics right now. Now, those are ice tectonics. So icy plates are subducting down into the ocean, being remelted and then refrozen and producing new crustal material. But it's very, very Earth-like in that way. So we've got water, we've got chemistry, and we've got energy. And I think the other thing that we never really talk about, but we should on Europa, is that we've got history. If you imagine the Earth and Europa 4.5 billion years ago, the ocean rock interface is almost exactly the same. It's a saltwater ocean. It's reacting with a hydrothermal system to maybe create biochemistry to support life, or prebiotic chemistry to support life. So 4.5 billion years ago, Earth and Europa, we know, are very similar in that way. And so if life got a chance, took a foothold at that time, I think it's got a real shot today. And so with 2 different missions, or at least right now, Europa Clipper, potentially Europa Lander, I think we've got a chance in our lifetime, so we like to call it life in our lifetime, right, to be able to actually land and ask these questions. So that's why I think Europa's our place.
Thank you. Maybe your lifetime, Brittany. Svet is up next, and let me tell you that in addition to being a devotee of the Red Planet, she extends her scientific expertise into the kitchen, cooking, I assume, and salsa dancing, and presumably sometimes both together.
Maybe. So I have my money placed on fossil life on Mars, and I don't mean like dino fossils. I'm talking about microscopic microbial, so bacterial life on Mars. And I have 4 reasons for that. The first reason is because of what we understand about the fossil record on Earth. If you counted all the carbon atoms that are alive in everything that mushrooms, trees, elephants, everything that's alive today, and you compared that to the carbon atoms of everything that's ever been alive and then has gotten fossilized and preserved in the fossil record, you would see that the difference, that ratio, is about 10,000. So 10,000 more carbon atoms of everything that's ever been fossilized compared to everything that's alive today. So that's the first clue why I think fossils are a better bet than looking for living life on Mars. And we also understand a lot about those processes that protect those delicate carbon atoms and preserve them through the geological forces of time. We understand what kind of mineral environments are favorable for the preservation of carbon, of organic matter on Earth. And so I think it's not unreasonable to extend those same principles to Mars. And that brings me to my second reason. Because Mars has had all of the ingredients necessary not only to evolve life, but all of the environments, the diverse environments necessary to preserve that life through geologic time. We know Mars was warmer and wetter in its past. We've all seen those, those silly memes with the cup of water and the Mars candy bar underneath, water on Mars. And it's not funny anymore, it's not cute anymore. And the reason is because we get it. We get it. We know there's a lot of water on Mars. All the rovers that have given us information about the habitability of the environments that they've explored have repeatedly confirmed to us that Mars had the conditions, the ingredients for life, the water. So it was a favorable place for evolving and also preserving life if it had evolved. We know that those same kinds of mineral environments, those characteristics in those environments, like, for example, fossils tend to stay preserved in environments, in minerals that are not very porous. So you don't have fluids circulating through and degrading and washing away and altering the fossils. Those kinds of environments exist on Mars as well. And my third reason is the reason why we know all of this about the environments on Mars. Because of the continuous robotic exploration of Mars since 1997. Of course, we've been launching things to Mars since much earlier than that, but we've basically had our eyes on Mars continuously in the form of rovers, landers, orbiters since 1997. And I think the momentum is only building, and it's only going to get more interesting in the next decade. I think starting in 2020, we're going to usher in a new era of very exciting exploration on Mars. Because in 2020, there are going to be 2 rovers that are going to be sent. NASA's Mars 2020 rover and the European Space Agency's ExoMars rover. And these 2 rovers are going to be designed to fully focus on looking for signatures of life, looking for biosignatures on Mars. And that is something that most rovers and landers that have been on Mars have not been designed to do. So stay tuned, because some very exciting things are going to happen on Mars starting in 2020. And also, let's not forget the private space sector. Do we have any SpaceX fans in the house? Yeah, go SpaceX. It's not unreasonable to think that perhaps human exploration of Mars, which is a possibility in the near future, is going to be how we're going to find those signs of life, as opposed to robotic exploration. And my 4th and final reason why I think it's going to be fossil life on Mars is because we already have lots of freebie samples from Mars delivered, gifted to us by nature in the form of Martian meteorites. We have a lot of meteorites on Earth from various places in our solar system, and some of them, a small percentage of them, come from Mars. And the really cool thing about some of these Martian meteorites is that they contain complex carbon structures, not necessarily formed by life, but still carbon structures that allow us to test our hypotheses about, for example, what we're seeing on the rovers and what we're going to see when we bring back samples from Mars to Earth, because the 2020 rover is actually going to bring samples back. It's going to cache them and return them to Earth for study in more sophisticated labs on Earth. And so you can't say that about any other planet in the solar system. That's why I think it's going to be fossils on Mars.
Thank you very much. Our speakers are doing very well. Nobody has tripped up yet, going up and down the steps. So next up is Sarah, who many of you will know as Astrobiology's finest stand-up comedian.
Oh.
She also holds the world record for rapid delivery, and she will explain the slide.
Oh, great. Yes, I'll get to the slide, which Paul actually made for me. Thank you very much, Paul. So how many people in this room are alive? I think everybody probably is. Okay, so we definitely know there's life on Earth. Now the question is there alien life on Earth? And so the question that we're asking scientifically is not whether UFOs are visiting us, but whether there's actually microbial life or some other kind of life form on Earth. Now the reason that's interesting is everybody in this room probably should have raised their hand when I asked if they were alive. I guess some people weren't paying attention. Or maybe they aren't alive, I'm not really sure. But everything on this planet, as far as we know, is related biochemically. So the chemistry of living systems has a commonality to it. And so when we're talking about living systems on Earth, life on Earth, we think all life on Earth is related. At least all known life on Earth is related that we've discovered so far. So could we actually find life on Earth that has a different chemical makeup? Maybe something like a shadow biosphere is the name that it's called in the scientific community. And so this is actually a picture of Shadow Paul. You'll notice that Paul is looking at himself as if he's in a mirror. This is because one of the proposals for shadow life is what is called mirror life. And so if you raise both your hands, you'll notice that they're mirror images of each other. Biomolecules that are inside your cells are also common mirror image varieties, but in living systems, we have only one form of them. And so one question could be, could there be life of the other form living on Earth? So there's a whole bunch of different proposals about what kind of different chemistry could actually coexist on Earth with our own biochemistry. And you may ask, well, why haven't we found this life yet? And the reason is that when we're looking for life on Earth, we are not looking for things that we don't know. We're looking for things that have DNA, primarily. Most of our life detection actually involves DNA. So why are we not looking for things that we don't know? Any guesses? It's because we don't know. The whole reason we have this panel today is because we actually don't know what life is, so we don't know how to look for it, we haven't found it yet. And so one of the things I actually work on is trying to understand what living systems are. What is life? That's a great question. And so my conjecture is that until we have an understanding of what life is, and by that I mean an actual theory of life, some kind of quantitative framework for understanding life that goes beyond just the chemistry of life that we know it, but is predictive of other chemistries, we won't be able to find life. But when we do have such an understanding, the easiest place for us to look will be on Earth. And we already know life happened here once, so why not look and see if it happened again? And that is my argument. Thanks.
Thank you, Sarah. Thank you. And so now we move on to Jacob, and still fairly close to home, as you'll see from the picture here. And I should mention that in addition to his many talents, if I got the information correct, Jacob is setting up a lottery bond to fund the search for ET. And if you ask him nicely, he might sell you one later on tonight. Jacob.
I'm still looking for investors in this, so if you have a lot of money, come and talk to me. But we live on a planet, as you can see from this picture, that has been modified by technology on a global scale. This is the black marble, Earth at night. And you can see there's very small regions of Earth that are untouched by civilization at this point, some places. Now, imagine that you are an extraterrestrial astronomer some distance away from Earth, 10, 20, 30, 40, 50, 100 light years, take your pick. Maybe not 100 light years, let's say 40 light years. And you build a big telescope, you've got great funding, you point it at Earth. You're going to see, maybe not exactly this, you're going to be able to detect evidence of our technology at a distance if you're looking right. City lights, if you look the right way, you could detect evidence of that on the dark shadowed side of a planet. This is not the only signature that's coming across from our planet, but it's the most visual one, and so it's a nice one to start with. Radio waves are another important signal that have been emanating from our planet. I don't have a nice picture like this yet of Earth from the radio wavelength on a global scale. I would like to someday, actually. It'd be really interesting. But we've been emanating radio waves for roughly 100-some years, mainly in the form of television carrier waves as well as radar, mainly for military purposes. All of these electromagnetic waves travel at the speed of light. They're carrying information about our technological civilization to any observers that might be watching. So now we turn the question around. With SETI, the search for extraterrestrial intelligence, what we're looking for is not just intelligent beings, but intelligent technological beings that we could detect at a distance. And by anything that we could detect has to be conceivable to us. So we're really looking for some sort of mirror image of ourselves, either now or sometime in the future. So if we were to find something like evidence of city lights or evidence of strong radio transmissions from another part of an exoplanet or a star system, this would be very strong, almost unequivocal evidence. If you get the signal right, if you have a strong detection, this would be very unequivocal evidence for intelligent life elsewhere in the universe. So what are we doing? How are we looking for this? Well, SETI, the SETI Institute has been working on this since the 1960s, 1970s. Frank Drake made the first observation of some nearby stars in Project Ozma, and obviously didn't find anything. But what Jill Tarter of the SETI Institute likes to point out is that up until this point, SETI is like swimming. If you're in a boat in the middle of the ocean and you've got a drinking glass, and you ask the question, are there any fish in the ocean? And you take your drinking glass, dip it into the water, and you look in your glass, and you don't have any fish. Well, what have you proven? You've not proven that there are no fish in the ocean. You've proven that your one experiment is unable to detect life. Maybe you need a bigger glass. Maybe to look somewhere else in the ocean. So the amount of search space that SETI has done right now is so drastically small compared to the vast scale of the universe. But here's the good news. The good news is that recently there was a billionaire who got very motivated by this question. Yuri Milner and some of his entrepreneur friends started the Breakthrough Listen initiative, which is a $100 million initiative to do the first full sky survey for SETIs using the Green Bank telescope in West Virginia and the Parkes telescope in Australia to do a full radio survey of both hemispheres, which has never before been accomplished. In addition to that, they're also going to be looking for little laser pulses, which is another way if an extraterrestrial civilization was attempting to communicate or somehow signal their existence. So these are ways that we know can travel through space relatively unfettered without losing the information that would give us a very clear signal of evidence of extraterrestrial intelligence. So this is starting now. You're going to be hearing about breakthrough listen over the next decade, and with any luck, there will be at least some interesting signals to follow up on. Other encouraging news is the SETI Institute, their flagship array, the Allen Telescope Array. For a while, the SETI Institute was struggling to fund this. They now have a partnership with private industry who uses it half the time, but fortunately they pay for it. So the SETI Institute has a nice deal where they get to use this telescope every night with very low costs. And you get to do really good science. And so the combination of the Allen Telescope Array and the Green Bank, or the Breakthrough Listen Initiative, this is going to be the best attempt at searching the skies for evidence of extraterrestrial intelligence. The last point is there's a very strong tie into exoplanet science here. I think doing a full sky survey is great. We've never done this before. It's going to give us a lot of information. But I think the best way to do this is the exoplanets that show strong signs of habitability, good candidate planets in the habitable zone, maybe even if we see biosignatures. I think those are going to be the best targets to follow up for with SETI, to listen to see if we're really not alone. And that's why I think SETI is going to be the first discovery of extraterrestrial life.
Jacob, thank you. And finally, we move on to Charlie Lineweaver, about whom words fail me, but they're rarely known to fail him. Charlie is, I think, the most disagreeing, I didn't say disagreeable, the most disagreeing person I know, and we thought it would be good for him to bring up the rear and probably rubbish everything that has been said so far. So,
you flatter me, Paul. You flatter me. All right, so my mission is to describe that, defend the opinion that we will never find life as we know it. And I think also defend the somewhat schizophrenic opposite, and that is I think we possibly have already found life as we don't know it. Now, why those two things are not mutually exclusive is because we don't know what life is. So there's a biologist, about 50 years ago, named J.D. Bernal, who talked to Einstein about this. And I'm a physicist, so I always listen to what Einstein says. And Bernal said that Einstein thought about this a little bit, and he said that, you know, if we want a definition of life that has any chance of defining life elsewhere, then it would have to include many features which we now consider, life in a very poetic way. And I think we should take that seriously. And one poetic vision, or kind of a weird vision, is something that Ilya Prigogine talked about, and that is a far from equilibrium dissipative system. Fancy words, far from equilibrium dissipative system, like a hurricane, or a tornado, or a volcano, or a convection cell, or the life forms in this room. And all of them are doing things that are well structured and they're producing entropy. So that's one kind of weird definition of life that many people are uncomfortable with. But I think if we define life that way, then we have already found life elsewhere. We found a red spot on Jupiter. We found stars burning. We found whirlwinds on Mars. And so if you're willing to take that, I guess, a poetic jump and say that's what life is, well, then we've already found it. So that's one vision. On the other hand, if we're looking for life as we do know it, I think we'll never find that. And it's kind of like looking for English-speaking aliens. I think most people say, oh, English-speaking, that's crazy. Don't go looking for English-speaking aliens, because English is so quirky. But I think the idea that life is some type of generic thing is something that doesn't have much evidence. We have one example here, and that could very well be as quirky as the English language. Now, if I were up here saying, oh, we'll never find English-speaking aliens, most of you would agree. But because you've been propagandized into thinking life is generic, as are most biologists, then you say, oh, well, we'll find it. So it really depends on whether it's quirky like English or it's generic. But the most generic thing that physicists are comfortable with is, in fact, far from equilibrium dissipative systems. So you might say, well, if the answer to this question is so ambiguous, depends on the definition of life, well, maybe, Charlie, you need a better definition of life. And I would say, no, I don't think defining life is very helpful. In 2012, a Nobel Prize-winning biologist named Jack Szostak wrote an article saying, it's not helpful to try to define life. One of the ways you can understand why it wouldn't be helpful is imagine trying to define, oh, let's look for eyeballs. How old are eyeballs? Let's go back let's get in a time machine and go looking for eyeballs. Go 300 million years back, 400, 500, 600. As you go back, what became eyeballs gets deconstructed. They get, proto-eyeballs and proto-eyeballs. And anything that has evolved on this Earth is the same way. You can think of a head. Okay, go back 500 million years, 600, 700 million, heads disappear. They really get deconstructed if you go back in a time machine. It may be the case, I think it might be the case, that life also gets deconstructed as we go further and further back. And we should not trust our current definitions of what now we call life as something that's platonic like pi or 2. And life is not like that. Life too is something that has evolved. And if that's the case, well, current versions of it are not something that we can trust in the early Earth and also elsewhere. So I have of the opinion that we will never find life as we know it, and we have already found life as we don't know it.
Wonderful. Thank you very much. Well, we're going to develop one or two of these themes for a while before taking questions from the audience. And let me start off by saying that the question whether or not we are alone in the universe really hinges, in my opinion, on whether life has happened more than once. And that's been the implication running through our remarks. But there is a complication, and Svet mentioned it, the Mars meteorites, of which we have several in our collection here at Arizona State University. If Earth and Mars exchange rocks, then they can also exchange microorganisms. And so this complicates the search for life within our solar system, and particularly for Mars, because we may go to Mars and find life there, but it'll just be good old boring Earth life. It won't be the second sample that we all crave. That could be a problem for the icy moons as well, but it's surely not a problem for Vicky's extrasolar planets. And so would anybody like to say this is not a problem? So Svet, I'm sort of challenging your position. Would you like to say that this rocky panspermia isn't going to be an issue when it comes to looking for life on Mars?
Interesting. I mean, I don't think that's a problem, because I would argue that whether or not life is the same genesis as we found on Earth when we find it on Mars or not, the fact that it was prevalent, the fact that it was preservable, the fact that it was detectable by us is quite an impressive achievement, and probably one of humanity's most amazing achievements, and that will have huge implications. So I don't think that's a problem.
You're not too worried about it. So Brittany, can Earth rocks get to Europa and contaminate it with Earth microbes?
There's a very
Oh dear.
Yeah, there's a
The
very,
beyond
very,
center
very,
just
very,
collapsed.
very small chance of that possibility.
Right.
It's very difficult to get them that far out.
Right.
It's certain that there was lots of material moving around through the inner solar system, and certainly through the whole solar system. But the other thing that you have to think about is not just, imagine the journey that material is taking. So you've got something that's been blasted off of one planet, and it's certain we've shown that organisms, tardigrades, for instance, one of the most fascinating ones, can withstand conditions in space, long periods of time being heated or frozen or relatively inactive, and then come back to life, or come back to their previous activity. But one of the things you have to think about is what happened to that rock to get off the planet. Finally, what happens to it before it gets to the other planet? And then there's a stark difference between surviving a set of conditions, luckily landing in conditions that you're capable of not only surviving in and of themselves, but then reproducing enough to then grandly populate an entire other planet. And so I think between the probability functions that we're talking about, that, at least for the icy worlds, it's probably not very large. I would argue it's not very large for Mars either, because that rock rock, these are megaton explosions that kick a rock off a planet in the first place. Has to survive off the Earth through its atmosphere, come back down at Jupiter's escape velocity on the surface of Europa. I mean, we're probably going to crash land spacecraft there because it's relatively sterilizing.
No aerobraking.
So then the organism has to survive somehow in an intact rock that's probably going to be a plasma at this point in time. But if it's not a plasma, then it has to get out of that rock into an object that's highly oxidizing, and then make it all the way down into an environment where it's no longer being irradiated at the surface. I think there's probably no chance.
I disagree with you, but I'm the moderator, so I'm going to keep quiet about it. And presumably, Vicky, it's not too much of a problem in your case.
Yeah, the probability of Earth life seeding life on Proxima Centauri b is probably very low.
Jacob,
Paul,
I want to leap to... Well, sorry, Charlie, do leap in, because
Could
it's
you
supposed to
be
be
explicit about what the question is we're trying to answer?
Well, the question is, yes, and I knew you would disagree with this. So, what we're really... I think what most people are interested in is not, as Bill Clinton said when he stood on the White House lawn after the Mars meteorite, about if we discover life on Mars, it will transform our view of the universe. It would only do that if you could show that life had started independently on Mars, that the probability of going from non-life to life is not incredibly small, because if you've got 2 samples of life in the solar system, surely the universe is going to be full of it. So the issue is not can life get from one planet to another, has it happened once only and spread around a bit, but is the transition from non-life to life something that is quite likely? And therefore, all those habitable planets that we're discovering are, as potential abodes for life, actually may have life.
Well, the reason I'm asking is because Svetlana answered your question by saying, well, it doesn't matter whether it has an independent origin, it'll still be something interesting. So if you're going to allow that into question, where will we find life next? You look in a journal next week about some new species that has been found by a biologist. That, I think, is definitely the answer to this question. We will find it in, biologists will find it, already has found it, and just will be published next week. That, I guarantee you, is the answer to the question, if you allow that type of...
Right, but we'd like
Yeah,
some
I didn't
different
cheat
life.
and use synthetic biology, and I could have. I was very tempted.
Can I change subjects totally and ask Jacob that you talked about SETI and remote signals and light years away and so on. What are the chances that during its 4.5 billion year history, the solar system has been visited by some sort of alien technology? That there was alien technology, not necessarily the proverbial little green men or little green persons, but some form of alien technology. And might it still be here? And how would we find it? How would we go looking for alien artifacts within the solar system?
Yeah, this is a great question and something I'm pretty sure I've thought about.
But tell the audience.
Yeah. So we humans have sent out probes into space, not for very long, since the 60s or 70s. But the Voyager probes, Voyager 1 and 2, they've basically left the solar system. They've left the region where the sun has main influence, and they're well on their way to becoming interstellar spacecraft. Now, they're not really going to land in another solar system. They're not on that kind of trajectory. But there's a demonstration of this technology. We can send spacecraft out to another star system. I mentioned Yuri Milner. Breakthrough Starshot is another project that he's funding at $100 million to send Gram-sized probes to Proxima b. So we already have a plan to send, they're going to build a giant death laser in the desert. So keep an eye on this project. It's got a lot of interest. But so we know we can do this. We can send probes to other stars and have in situ observations. So there's no reason in the 4 billion year history of the galaxy, of the solar system, there's no reason that other extraterrestrials wouldn't have found interest in Earth. Oh look, there's this rocky planet forming in a habitable zone with some water. Maybe they like gas giants. Maybe they're like, oh look, there's a Jupiter with some rocky moons around it. We don't know what they're interested in, but it's very conceivable that something like that could be in our solar system. We would have very, very low chance of finding that now. I think you would want a very systematic search, look at stable Lagrange points or orbital places where you can have a satellite stable for longer periods of time. I think there's some systematic searching you can do in the solar system, but I guess what you have to be careful of is there's a philosophical argument called Russell's teapot, where I could hypothesize there's a teapot in orbit between Mars and Jupiter, and you go look for it, and you come back and say, Jacob, we didn't find it. Like, oh, well, it's smaller. It's a smaller teapot. You weren't looking hard enough. And so you have to be careful. Yes, there could be alien artifacts in the solar system, but at some point, if you're looking and you don't find them, you can't keep insisting that they're there just because you haven't found them. But it's totally conceivable, and I think we should keep looking for this.
Could I push back
Yeah,
on that? What the
well,
main
I'm
assumption? Well,
pleased you are.
I forgot to mention that this slide here, and
You did.
I think that the reason I put up that slide is because I think that our closest relatives in the universe are here on Earth, and there's Jane Goodall with our closest relative, the other species, a chimpanzee, and what we have done with outer space is we have projected ourselves into the universe, and that's what we see here, all the aliens that we have done on TV and in books. And that seems silly, and I've tried to make it silly, but it's not, it might be silly to project bacterial life that we have here and say, oh, it too could evolve there. I don't see that there's a major non-silliness to projecting Earth terrestrial bacteria elsewhere, any less silly than projecting this guy over here on the right. I don't know who he is, but so I think that the assumption behind SETI is human-like intelligence is a convergent feature of evolution, and we see no evidence for that on Earth.
Technology, not necessarily human-like.
Okay.
Just the general ability to build a radio transmitter.
Okay, there's no evidence for that on Earth.
Well,
That's a
all
convergent feature.
we really want is alien technology. And as we were talking about that, Vicky, let me just ask you, there's been a lot of interest, very speculative, in alien megastructures in other planetary systems. Do you spare a thought for that, or is it just the lunatic fringe of the subject?
Yes. Yeah, we do think about alien structures, and I was actually part of a project recently run by Lucian Wolkowicz to see if we could see them, for example, in transit signals. You can imagine aliens trying to give us a message by putting up particular craft that have very unnatural shapes, like triangles, for example, flying in formation, or things like that we could potentially look at. There's this thing called Tabby Star, which has a very unusual transit signal that people are looking at, and one of the hypotheses is that it's an alien structure of some sort. Of course, there are other hypotheses that are not as alien focused for that, and we're still trying to figure out what that phenomenon is. But yeah, those are the sort of things that we're always on the lookout for, really. And Lucian again is putting together software, sort of machine learning software that looks for the unexpected in Kepler transit signals to look for these sorts of things.
Sarah, you've thought a bit about alien techno-signatures. I know we should expect the unexpected, but do you have any thoughts about things that have not been mentioned that we might go look for?
I don't think we have a clue what life is, to be honest. I mean, that was actually the whole point of my argument.
Thinking of technology in particular, you see.
Yeah.
What might be a techno-signature that we haven't discussed yet?
Well, I mean, a classic one that people talk about with exoplanets is actually pollution. And Jacob's thought a lot about that. And so you might think about looking for planets that are very polluted, which is a very bleak view of what living things are doing on different worlds. So I think that's certainly one possibility. There's always classic things like Dyson spheres, which would be like, really massive megastructures around other stars. You could get galactic if you wanted to look for like special patterns of stars. If you think that like a really advanced technological civilization actually could move stars into particular
Kardashev level 3.
Yeah, maybe like a gravity slingshot or something.
Pulsar GPS.
Yeah, there you go, pulsar GPS. So I think one of the challenges with looking for life is the way we think about it is only bounded by our imagination, and that makes it really hard to do astrobiology as a science. But I think that's one of the things that's really incredible about the field is that we managed to do it, and it's because there's a lot of really creative scientists working on these problems that are really trying to figure out ways to think about these things critically.
Can I actually add
Yes,
something to this? So I like your comment about alien pollution, and to take it one step further, I think there is one techno-signature that we might find with exoplanet science, and that is a terraformed planet next to a habitable planet. So if we imagine Earth, Earth today is in the habitable zone, Mars is not really. It's not habitable because it's just too small. But you could imagine humans going to Mars and making Mars, raising the average surface temperature of Mars by putting chlorofluorocarbons in the atmosphere, something like this. And so Mars now becomes more Earth-like, even though at the distance it is from the sun, you would calculate that it should not necessarily be as warm as you observe it. So I think there are some technosignatures that exoplanet science could get us toward.
Gerrymandered planets, yeah. So before we bring in the audience, I've just got two questions, a quick one and one that maybe is a bit more contentious. The quick one is, anybody here prepared to speak up for Venus? Life on Venus?
Well, yeah, sure. I
Yeah.
mean, early. Since you don't know what life is, you can imagine it anywhere.
Yeah.
But no, Venus is the planet that's that used to be the most
That's
like
right.
Earth, right?
That's right.
So it's 0.7 AU. We're at 1 AU.
It all went badly wrong for them.
If you call a runaway greenhouse badly
Maybe
wrong.
they like it.
Yes, maybe they did it themselves. I do not know. So one of the uncertainties is when Venus went greenhouse. I don't know whether it was a billion. Maybe Vicky, would you know that 1 billion, 2 billion years ago?
We don't really, all we have is this evidence that 1 billion years ago we overturned the surface, and so it's not fully pinned down. And I know there's some people that think that maybe at the point that the surface overturn occurred, that's when the runaway occurred.
So-
but it could have happened a lot earlier, depending
So
on
let's
models.
suppose it happened
It's
2
not
billion years
constrained.
ago.
So
If it happened 2 billion years ago, then
Yeah,
hey,
more
in
than
2
a billion
billion years in which life could have evolved in a very similar way to the way it might have evolved here. So life on Venus is as likely as life here, maybe. But it just got killed, got heated up, got cooked.
All right, and now to the more contentious question, which is, and I think Svet already alluded to this, that the general public has the impression that NASA has spent decades searching for life on Mars, but we all know that the last biological experiment done on Mars, or indeed anywhere by NASA, outside of Earth, well outside of low Earth orbit, was Viking in 1976. And you mentioned that there are plans to actually do biological experiments on Mars and maybe sample return. So is this going to survive the rigors of NASA quality control? Do you think that they really are going to do, for example, like the labeled release experiment, repeat that on Mars? Is that in prospect, or is this going to be pushed off for another decade?
Yeah, so let's back up and first talk about Viking. So in the mid-70s, a set of twin landers, the Viking landers, were the first actual targeted biosignature searches on Mars. And there's been a lot of controversy about what they actually discovered. The Viking landers made the assumption that we were looking for specifically living life on Mars, microbes in the soil that were actively, metabolizing, actively living, breathing. And so the actual experiments were designed to measure only that. So that's a very strong assumption to make. And the other assumption that was made was that we had a very good understanding about the chemistry of Martian soil, that we knew exactly what the components were of Martian soil. And the problem with both of those assumptions was that the results of Viking were kind of both ways. Some of the results showed that, yeah, something's reacting in the soil that looks like life, like microbes. And some of the other experiments showed, no, there's nothing alive in the soil. So what do you do with that? How do you deal with that result? The community argued about that, and I think the more accepted response, the more accepted result is that there was something in the soil mimicking life, that there was a component in the soil that was mimicking life reactions. And since Viking, we've learned that that's actually true. There's a component in the soil, oxidants, or specifically perchlorate chemicals, that are actually attacking anything carbon-based or organics, and they're altering them and changing them in a way that's really confusing our interpretations.
So
that
my
was,
question is less what did Viking find, but more will NASA get over the shock of having that inconclusive result and actually send another biology experiment to Mars?
Yeah.
That's what I'm
So,
after.
right. So the point I was trying to make with that is that we made a lot of assumptions with Viking that we're not making with the upcoming biosignature searches. The 2020 rover and the ExoMars rover are not targeting their biosignature searches to specifically extant life that is metabolizing. We're targeting a variety of carbon-based components because we're going to have instruments that are going to do laser-based and other chemistry-based analyses. They're going to give us a diversity of potential signatures of life. And on the 2020 rover, we're not actually going to conclude whether or not there's life on Mars. I would argue that you can't really conclusively say whether or not you're going to have life on Mars with a robotic rover. So that is why the 2020 rover is actually going to bring those samples back to Earth. That is the NASA exploration strategy. And when we bring those back to Earth at a much later point in time, we're going to expose those samples to the more sophisticated techniques that we have available to us here that you can't put on a rover, and not making any of those assumptions that we made with Viking. We're going to have a much, much better chance. And we're going to have teams of people all over the world who are going to get those samples and are going to be able to do a variety of very interesting experiments with them. So I do think
if
we're
we
going to have a
overcome
much better chance.
the planetary protection and legal issues.
Or if we bring them back.
Right.
Is that, right now, that's not.
Or take them to the space station or
Not
something.
certain.
Yeah.
Can I make an extra
Yeah,
comment
yes,
on that?
and then we're bringing the audience. Yes, please, people. Yes.
Yeah, I mean, this kind of emphasizes sort of a major theme in astrobiology, which that it's very difficult to interpret a potential biosignature unless you really understand what's going on in the environment around it. And so the Viking experiments were kind of really a classic example of that. We were fairly ignorant about what the chemistry of the Martian soil was, and so we weren't able to interpret our results. And the same thing can potentially happen for exoplanets even. I talked about oxygen, but I didn't talk about the potential for false positives, which is ways that the environment could make oxygen and fool us. So this is a big theme in astrobiology now, is trying to understand what is the context of the environment we're searching in, how can that environment make the thing that we're looking for, and how do we tell the difference?
What would it take to convince a skeptic that that really was life that time?
Right.
I'd like to bring in the audience, and there you'll see the microphones either side. Please don't squabble. Form an orderly queue, as we would say in England, and I'll do a sort of left-right approach. So we'll start with the gentleman over there.
So when I was a graduate student, not too many decades ago, we were taught that exoplanets outside of the solar system was exceedingly rare, very hard to imagine. And I think the lesson that we've learned throughout astronomy is that to the extent that we think we're special, we're wrong. And every time we thought we're special, we have been wrong. I had two immediate responses to some of the comments from the panel. One of them is this idea that we couldn't really imagine panspermia working between exoplanets, but remember that the Oort cloud and its perturbations extend easily between stars, and comets are not a bad place to imagine putting biological spores. I think the other comment was about looking for signals on exoplanets. And the light signal is a good place to start, but actually the thermodynamic signal, heat generated by life, is 10 times larger with a much smaller background from the exoplanet. So it's just a cautionary comment that to the extent we bias our views by our own experience, I think we've been wrong.
Right, thanks. That really is a comment. So I won't sort of reopen the issue about panspermia because I think you gave your opinions. And I'll move to the question from the gentleman here.
Sure. Thanks for being here, everyone. It's been a fun discussion so far. It kind of dovetails off of the previous comment over there. I wanted to ask about what you said about far from equilibrium dissipative systems and how you said that there might be many such dissipative systems. Indeed, there are in the universe, but life is a very particular, unique, and rare one. And so the way I see it is that we've sort of learned and formulated a very generic story for planet formation. And we think that geology and geochemistry are somewhat universal. We see the same types of minerals on Mars. We think that there might be hydrothermal vents in the ocean worlds. So a dissipative system that would arise on a terrestrial body to tackle a disequilibrium it seems like those disequilibria or barriers would be kind of universal, in that each terrestrial planet would offer that for something like life as we know it to then emerge to tackle that and dissipate that disequilibrium.
Well,
What do you
would
think
say,
about that?
Well, I agree with everything you said, except for the part where you say that it would necessarily engender the type of life that we are all familiar with here. Now, if it engendered a convection cell, most people wouldn't be happy because they say, oh, that's not life. But so we have these blinkers saying we're looking for terrestrial life, and we always want to say it's a generic feature. You just assumed it was a generic feature when you said, oh, if you have these redox potentials and you have this thermal gradient, et cetera, you will produce the things that were at the origin of life on Earth. But you know what? English is here, and it didn't happen magically. It had very peculiar beginnings. And when you're talking about biology, you're talking not about astronomy anymore. You're not talking about physics. And so you're not talking about the deterministic sciences. You're talking about something that's very, very self-referential, not too different from a particular human language. And that quirkiness is something that I think we should entertain as a possibility for what type of life we think we have here, rather than this propaganda. It's generic, therefore it's out there.
So I would disagree with that.
Good,
and the
good.
reason that I disagree with that is two things. Is because language, you've picked English, but dolphins communicate, right? So that's an example of a completely inhuman evolution of language or of communication.
Wait, stop. We and dolphins have a common ancestor about
that's
95
true.
million years
That's
ago.
true,
So that's
but
not anything.
Okay,
We are
yes, but
animals.
I'm giving
We
you
have
the
same
example.
organs.
You've chosen English as your example, and I'm giving you other examples. And the fact that we've evolved multicellularity and multiple other opportunities. But I think you're oversimplifying what people are doing to look for biosignatures. And one of the things I think is the major advance, and in fact perhaps it's Viking that taught us this lesson, was that we can't overprescribe the system. And we're trying to use the systems that we look at from a physics perspective. I too am a physicist. From a physics perspective of what are the available pieces of the puzzle that we can understand, and how can we make them productive but generic enough that we could then discover them. And I think some of the coolest lectures that we've seen so far at AbSciCon are in the ways to make biomarker detection generic, in which it's not prescriptive of the types of things that we do. It's not our cells, our DNA, or any of these things. And so my greatest hope is the work that folks like Lee Cronin are doing, where you're looking at the statistical distribution of things that are products of life. You're not specifically saying we need alanine or a particular acid or an amino acid or a fingerprint or a filament or something like that. You're saying what are the things that might be the generic properties of life. And when you look at it that way, when you look at planets have convective cells, they have cores, they have activity, they have geologic activity, they have atmospheres. Those processes, if we can understand those as generic, I can recognize a Jupiter, right? Vicky can recognize a Jupiter. We don't need the Great Red Spot to tell us that it's Jupiter or it's Jupiter-like. And so in that way, I think we are actually learning from Viking that being overly prescriptive and very anthropocentric does us some disservice. But we're trying to still go through that process. So I'm a bit more optimistic that, as you suggest, that these general concepts between the similarities of planets and looking for those fingerprints gives us a clue as to what we should look for, and then a way to unspecify our looks at biology and the way that we're looking for something. Because if we're looking for English, you're right, that's not the right thing to look for.
I agree with almost everything you said, except non-prescriptive means looking at these far from equilibrium dissipative systems and say, oh, look at that, we found life.
Yeah.
That's very non-prescriptive.
But that is, and that's what Mike's saying here, I think, is that if a disequilibrium exists, then that's your point to go in. And for exoplanets in particular, that is one of the things we would particularly like to look for is a disequilibrium in the system. When the Galileo spacecraft flew by Earth, it was able to measure the abundance of gases in the atmosphere and go, whoa, that system is not in equilibrium. It's clearly out of equilibrium. And the disequilibrium itself is not the signal. It is the fact that there is a disequilibrium means that there are active fluxes at the surface of these gases, active fluxes somewhere in the system. And that's the point at which we go in and say, we seem to have an awful lot of oxygen coming on this planet.
I'm
What
going to
produces
pull rank and
that?
truncate the discussion, because
All right.
when you get into an argument with Charlie, you can go on all night.
All right,
And there's people patiently
Anyway,
waiting. So I'm going to take the next
think we can
question
be
from
generic.
over that side.
Hi, I'm with the, excuse me, I'm with the New Mexico Museum of Space History, and a 3-hour drive away from us, of course, is Roswell. We know we're not going to find anything like those chaps on Mars, but you're talking about bacteria. How complex might life on Mars have become. Could it have become multicellular? Could those cells started to have specialized into rudimentary organs? I doubt we'll find anything vertebrate, but how far along might it have gotten? How high might our expectations reasonably get?
One,
Yeah.
one answer is that, that Carl Sagan tried to put floodlights on the Vikings so he could see giraffes or something that come up at night. So, but go ahead.
Carl Sagan actually tried to characterize four different ecosystem niches of organisms that were expected to be found with Viking. I remember reading a paper by Carl Sagan and a colleague of his right before the Viking landers landed, trying to figure out what kind of environmental conditions those very specific organisms would have. But if I remember, they were not more advanced than fungal systems. And so the reason why many of us think that whatever evolved on Mars, if it evolved, is going to be sort of microscopic, microbial, not too advanced, is because of what we know about Mars habitability in the past. It used to be warmer, wetter, much like the Earth, abundant water, abundant nutrients, all the ingredients necessary for life. And then very quickly in its history, the environment changed, the atmosphere sort of thinned out. There didn't seem to be any evidence of subduction for most of Mars history, if ever. And so when the conditions changed, Mars became cooler, not hospitable to the kind of life as we understand it today, and as we understand life evolved on Earth today. So if we're assuming that life on Mars evolved similarly like life on Earth, then those conditions became uninhabitable pretty early on. So that didn't leave too much time for life to get very complex.
Right.
And if sorry.
Yeah, no,
And
I think we need, I know what Charlie's going to say. What have you got against fungus?
So I mean, fungus
What's
I think
wrong
is
with
a
fungus?
bad example because it's actually fairly complex.
It is, rather.
But I don't think there is life on Mars at all, and hasn't been in the past. I know,
complexity zero.
Fighting words. But the reason, because we're supposed to be provocative, but the reason is that I think either life takes over an entire planet or it's not there. And so I think to answer the question, you certainly wouldn't have multicellular life, for example, because that's fairly advanced life, and I think life would have probably covered the surface of a planet and led to global feedbacks and dramatically changed the planetary surface before you actually had the evolution of multicellularity. And you can use the example of Earth for that. But even if it was microbial life, you might have also expected Mars to look quite different because of the presence of life. So there's often the assumption that Earth is habitable because it has water and it has oxygen and all these nice things, but most of the features of the surface of this planet are actually generated by life. And part of the continued habitability of our planet is the presence of life. And so Mars clearly doesn't have that, and I would imagine that life could not have gotten very far on that planet because of
But
that.
Jacob, what about an alien artifact on Mars?
It's worth looking. Look on the moon, look on Mars, but to be honest, we've mapped the surface of both of these bodies pretty well.
We have,
I think
who's looked at the pictures in enough detail?
So can I just throw in one more?
Put a
little
student on that,
curveball?
yeah.
I'm going to throw in one more curveball
Briefly,
into that.
because we must move along. Yes?
If we think about life on Earth, and the fossil record of life on Earth, it is largely photosynthetic. So surface life that is, using energy from the sun. And if we can imagine a biosphere that was not photosynthetic, it would probably look very, very different on Earth, and it would be much less abundant on Earth. So what if we applied that to Mars and thought, it could have just been a different type of metabolism. It could have been just a less abundant type of life. And so when you think about that possibility, maybe it's in the subsurface. Maybe it's where we're not able to detect it at the surface because we don't have the technology to currently go and look, tens to hundreds of meters into the subsurface where, if there's liquid water, that's where it would be on Mars today.
We do, but I won't get into it.
NASA doesn't.
All we need is is a 20 megaton bomb, and and we can easily get into that subsurface.
Good idea, Paul.
We need to speed up both the questions and the answers because we'll be thrown out of here in 15 minutes max. So yes, you sir.
All right. On exoplanets, if you detect two neighbor planets on a solar system, if both have the same atmospheric composition or maybe temperature, I don't know, could that be a sign of terraformation? No, it's not terraformation of one of those planets and a sign of extraterrestrial life?
Jacob, you'd like to?
Yeah, that's right. I think that's very accurate. I mean, I think if we were to find a planet, what we can do with climate models and observations is we can figure out, what the distance is of the planet from the star. We can figure out what an equilibrium surface temperature is. And if we've got spectra, then we can actually figure out what chemicals are in its atmosphere, and we can use models then and figure out what its surface temperature should be. If we do that for one planet, you do it for another planet that's further out, and you find they have the same surface temperature. Well, that's kind of weird if one planet is further away. Now, I think certain chemicals would be a better giveaway for terraforming than others. Something like chlorofluorocarbons are much less likely. I don't know of any abiotic processes that can generate these kind of things. If you saw an atmosphere with a dense carbon dioxide atmosphere, there might be an abiotic way of generating that. So I think it's going to be what specifically are we seeing in the atmosphere of these two planets that would lead us to think one is a technosignature. Right. But I think there's lots of ideas. Geoengineering is another one. We're thinking about doing that here, putting dust in the atmosphere to fight off climate change. There's things like that you could maybe imagine seeing around exoplanets.
I would like to agree.
Quickly, Charlie.
Yes, I would like to agree with you on this, Paul. That you have often said that the technological lifetime. You mentioned terraforming. Now we started to be able to do terraforming maybe for 100 years from now. But the singularity is approaching. The robot overmasters will soon take over what we think we're in control of. And if that's the case, they don't need the temperatures or they don't need to terraform anything because they live in outer space. And so maybe 99% of the lifetime of a technological civilization doesn't need those types of things, and so it would be a very small fraction of time that you would expect to see that.
Question from over there.
So you were talking about how life might be quirky and you can't say it's generic, and obviously you can't just if you send something to Europa and you send something down there, you can't just necessarily say I can call it when I see it about life, because that might not be how it would look like. So how would you be able to differentiate between some geologic feature, say on the seafloor of Europa, or between some kind of organism that might be like a slime mold, where there's not necessarily one single cell there, it's like a bunch of nuclei, they're all part of this one organism, but maybe it doesn't look, very like a slime mold, but more like a rock. Like, how would you
Brittany,
tell?
can you, if you get down there, it's slimy, what are you going to do?
Well, I'd be really excited if it was slimy, because that would be really fun. So I think the big question is that we're expecting to be relatively ignorant, right? There's some systematic things that life on this planet does uniquely, and one of those things is to make really big stuff. In terms of complex chemical molecules. And so that's one of the first things that we'd look for is actually, do we have really heavy, really long chain things, right? So there's mission concepts for both Europa and for Enceladus to look at materials coming out of those places and look at their fractionation patterns, and what does that tell us about the thermodynamics in which that chemical system evolved, and in turn, was it biology perhaps that did it? Now, but none of those is really a smoking gun. It's like a worm gun, or it's kind of a gun over there, and maybe it's not a gun, but maybe it's a water gun, who knows? But what you want to do is you want to build up a set of pieces of evidence, right? Ask many questions at the same time and say, what are the things that life might not necessarily uniquely do, but what are those fingerprints of that? And let's test for lots of them at the same time using the best technology we have, which is admittedly needs more advancement. And so the idea is that you can look at the molecules, you can look at structures, you can look at the history of the inorganic system, and you can look at how the thing has been processed or how it got there in some ways. And then what we're really looking for are things that are surprising, right? So things that are surprising not so much as like, oh, well, that's great, we have this chemical that we've never seen before, but things that were surprisingly out of equilibrium, which are the things that we've kind of talked about. And so life is really great at throwing things a little out of whack. And so if you're looking at something like that, then that gives you a really good chance. So you're trying to check as many boxes as possible, because at this point in time, we don't have a tricorder, right? We don't have something that's like, yes, that thing, life it shall be, right? So we want something like that. And so I think the best chance is to give ourselves a way to think about the information that gives us a chance to test in a lot of different directions. And it's not unique to what we're going to do on Europa, right? It's what we're going to do with exoplanets. It's what we're going to do with intelligent life, right? We wouldn't just see one chemical in the atmosphere and say, yes, absolutely, there is like New York City B sitting on this planet. There's a lot of ways to think about that. And I think that's the kind of interesting power of the way we think about the problem right now.
No fish on Europa?
Hopefully, but I think it's microbes.
Yes, question from here.
If your goal were to encourage the people of Earth to have a grander perspective of their own planet, to think more long-term or to think globally, what kind of astrobiological discovery would have the best chance of doing that? What kind of positive or negative detection would you hope for?
Okay, that's
can I
for
start with that
everybody.
one?
Jacob, and then I'd like to hear from Sarah.
So I think a SETI detection of a radio signal or a laser signal or something that can carry information that you can communicate with, I think that would give us a much needed long-term perspective. If we found anywhere from Proxima b to something 10 or 40 or more light years away, something that we could conceivably think about communicating with, but there's this lag. If you're communicating 40 light years away, it's going to take 40 light years to send that message. So we detect a signal, we get together as humanity, we figure out what we want to say in response, how we're going to say hello, then we send the message. Now you've got to wait 40 years for it to get there, and then 40 years for it to come back, minus, plus the time it takes them to understand that message. But if we've already got that detection, if we already know they're there, we're going to be willing to wait, and we're going to come up with governance structures to figure out how to maintain our patience so that we actually do receive this reply. I think that would be an incredible discovery.
Sarah, is there anything other than the classic signal from ET that might get people excited enough to spend a bit more money on this?
Well, that wasn't the original question. I mean, I can answer that question. I was actually, so I did have I struggle with the idea of like we never discover life. What does that mean for humanity? And I don't know if that's a more does that empower us more or empower us less? And I don't have the answer to that, but it's just to go the other direction. So what should we spend our money on? Is that what you're asking me?
Well, no, the point is that this subject of looking for life beyond Earth sort of goes through stages where people are interested and not so interested. It does cost a fair amount of money. Is there some discovery that would really transform the field to the point where everybody thought this has got to be the highest priority scientific endeavor?
We find English-speaking aliens. If we find English-speaking aliens, that'll really...
Well, that just meant they were watching our television programs.
Other than detecting a signal from ET, which obviously would, is the Holy Grail, there's a lot of stuff in between.
Yeah, so I mean,
between that and nothing.
Right. So as I mentioned, I have a lot of disagreements with the life as non-equilibrium structures, and I mean disequilibrium in a lot of places. But one of the things that living systems do that Brittany already mentioned is they surprise us. And so I think the thing that is really hard about this endeavor is looking for the unexpected. And so I actually think the more interesting kind of discovery for alien life is not to find life on an individual world, but to find life in a data set, like a probabilistic sense that we know it. So we're thinking right now, let's build up as many lines of evidence in one location that give us a conclusive set of arguments that this is a definitive signature of life. But we don't know what any of those pieces are. We don't know how they're going to come together. But what we do know is how to predict in a probabilistic sense what the properties of different environments should be, because we know the laws of physics and chemistry pretty well. So could we actually think of ways to look for life not in one location, but in many locations simultaneously and look for anomalies in statistical data sets? So then you have this kind of weird paradox where you've answered the question, if you get a positive signal, that you're not alone, but you don't know who your neighbors are.
Right, so we know there's somebody or something out there somewhere, but we're not quite sure where or what.
Right.
But I think I'd settle
But I think that would motivate us. So that's that's something that we can do based on current science. Now, if we knew the answer to that question, but we didn't know what that life was, then we're really motivated to go and find out what it is.
Okay, now we really are down to, I think, that one question probably from each side. Let's see how we go. Short question, please. Short answers, please, panel. Yes, sir.
Well, there isn't a short question at this juncture,
Oh dear.
but I'll ask it anyway. So here it goes. It's to do with the redirecting the resources. And this is particularly directed towards Jacob. Obviously, the rest of them can join in if they want to. Here's the thing. You said something about the radio wave being 50 years old and they're all about us, and other life form elsewhere in the universe could actually detect us. Now we know that for a start that we now have satellite. We don't have radio waves per se. So that means the signals are dying down. So now I'm now predicting that let's assume that there are life forms out there which you're trying to detect. In order for, and we also have to assume that it took 4.5 billion for the life to evolve. So that means the life elsewhere in the universe has to have started 9 billion years ago. Then it moved forward to 4.5 billion years ago. That life started on that planet. And that planet would generate less radio waves, because we're in a technology.
So can we move to the question, though?
The question it is in the next line, it's next punchline. I could have asked it by now, right? So the thing is, you will not be able to detect, because it would have taken 4 billion years to get the radio waves to this point here on planet Earth. You will not be able to detect it, and therefore you could have redirected your resources in other areas of research. That's my question.
Right.
Although,
rather than looking for radio messages, which are just a fleeting part of planetary history, what can we look for that has more longevity?
Right. So there's a couple things. Radio, you might be right, might be on its way down, on its way out, but we actually have quite a bit of transmission still going on. Even though we have digital television, we still have digital television transmissions, and so there's still quite a strong radio signal emanating from Earth. But another thing to think about is we still have sailboats on Earth, even though our military no longer relies on them. Sailboats, as an example, sailboats do not represent the pinnacle of our current technology, but there's still plenty of sailboat hobbyists. So I imagine extraterrestrials may go completely digital, they may be radio silent. That doesn't mean radio technology will be gone. We have ham radio operators today. They're going to be ham radio operators 100 years from now, even if we're not broadcasting into space. So we might not detect radio leakage like we would have from Earth, but if there was a direct beacon of some sort, that is something we could detect.
Right. Okay, I'm going to take one last question from here. I'm sorry about the gentleman over there who was waiting, but I think we're running out of time.
This isn't really a question. It's more like,
Oh, dear.
you said that most of Mars has been looked at, right? That was you, right?
Yep.
Okay, cool.
Photographed.
Yes.
Yeah,
And I said,
it has been photographed.
I said it hasn't.
Definitely
But,
photographed, but not looked at.
Like Phil Christensen, for example, I just got out of his class where he talks about Mars, and he said, like, it hasn't been looked at closely at all.
Right.
Really?
I think we should look closer.
Yeah,
I agree with you.
Nor has the moon.
One of
Say
his
we looked at most of Mars.
grad
definitely.
students just got published in Science because they zoomed in and they found swirly lava. So
Right.
No,
yeah,
I definitely agree
actually,
with you.
JMars is free and you can download it and you can just zoom in. So that's it.
I agree
Thank
with you.
Thank you for that comment. I think, much photographed but little studied, I think.
Well, we're talking about different scales. Photographing it from orbit is very, very different than getting up close to the micron level that you
Oh,
really
yeah.
need
No, we're not,
to detect microfossils.
Yeah,
and
but
that has not been looked at.
alien artifacts.
I think very large alien artifacts we would have seen by now.
Yeah.
But there's a threshold that's
Right.
very believable that you need to do more analysis to rule out.
Okay. If you could ask your question in 30 seconds and we get a 30-second
Okay,
reply, then we can go with it.
I was thinking that here on Earth, life started in a thermal vent, volcanic, then it moved to the Earth, to the ground, and
Right.
all. And
This is
there's
gonna be
so
more
many
than 30
ways
seconds,
life
so-
can evolve. So can you go with that?
Oh, well, was there a question there?
Oh, okay. I mean, if I'm saying is, we crawled all out of the earth, ocean.
Yes.
And we evolved into what we
Right,
are now.
right.
There's so many ways of evolution, and you were saying the evolution on Earth. You know, we could have had really smart people in the ocean.
There could be, and this is a much discussed subject where, you know, on a water world, whether there could be very intelligent but maybe non-technological aliens, super dolphins or something.
Too many ways to go.
Superfish. I feel that we're sort of opening up a can of worms at this very late stage, because unless somebody is really desperate to answer that question, but the next and last order of business was going to be to take a vote on whether anybody actually won this debate. So unless you're going to overrule me, I just would like to see one by one a show of hands, starting with Vicky's position that exoplanets will win this race. That's where we will discover life beyond Earth first. I'm not in a position to be able to count. I can only count up to 5. But I think we're
some people
all right.
from other
We'll have
camps
some sort of
I'm
estimate.
changing camps.
Can I vote too?
See where my allegiances lie.
Brittany, what about the ice worlds? Who prefers that? Well, I think that's slightly ahead so far.
That's what I like
Okay,
to see.
and Svet, life on Mars, always been my favourite, so I'm going to vote for that one. Oh dear. So Jacob, I guess we're voting for. Will we find? Oh, I'm sorry. How can I forget you?
Because I voted for someone else.
That's right. It confused me. So
easy
will
to
we
do shadow
find
life.
alien life here on Earth, first of all?
It's okay if we make
And
it.
actually, I'm voting for that one as well.
Trying to get more votes.
It's certainly more accessible if it's here. All right. Sorry, Sarah. Jacob, so we're voting, will we find basically an artifact before we find a cell? Who would like that? Okay. All right. And last but not least, who agrees with Charlie that it's all ridiculous? We're not going to find any life as we know it beyond
we've
Earth,
already found it, or we've already
or
found
that it's everywhere and it's a non-question. Does anybody like that position? Yeah, not too many. Actually, I lost track of who won this.
I think Ocean Worlds won.
I think we won the Ice World. Anyway. My thanks to everybody who has come this evening, and particularly members of the public. That's always very welcome. Thanks to NASA, the NASA Astrobiology Institute, and the organisers of the conference. And last but not least, my thanks to gallant panelists. One more round of applause, please.